It is part 2 of a review for chapter 8, techniques of integration. So far, we have required for definite integrals to satisfy two properties. The domain of integration must be finite, and the range of the integrand must be finite on this domain. However, in practice, we may encounter problems that fail to meet one or both of these conditions. In either case, we say the integral is improper, and we'll try to evaluate it as a limit. Let's see this definition. This is the case when the interval is infinite. We have three subcases. F is defined on the infinity, from a to infinity. Now we try to get here the integral over the infinite interval. Then first we'll get the definite integral from a to b, and we try to take a b approaching infinity. Okay, let's see a picture for that. Here, f is defined from a to infinity, and the value is given like that. Then, here from a to b, some point b, we try to get integral. Then, from a to b is finite no matter what it is. Once it is a determinate number, then it's finite, and then we can get the integral, definite integral, by using a conventional technique. And after getting the integral, we try to take a b approaching infinity. So that's the way of getting the infinite, the improper integral over infinite interval. And similarly, when f is continuous from minus infinity to b, then we try to get integral from a to b, and then take a limit as a approaches minus infinity. Once the function is continuous over whole real line, and if we have to get the integral over the whole real line of f, then for any real number c, and we have to get left side integral and right side integral, and both the value exists, then here the sum will be the final result for the given integral. For this portion, we have to use this technique. For this portion, we have to use that technique. Once the limit exists and finite, then we say the improper integral converges. Otherwise, the improper integral diverges. Okay, here, for what values of p does the integral converge? Okay, as given in this hint, we'll consider two cases. P is 1 and p is not 1. Okay, number 1. Okay, p is 1. Then the given integral is along with the limit b approaches infinity, and from 1 to b, now that is 1 over x and dx. P is 1. So for this one, the antiderivative is logarithm absolute value of x. So that is here same limit, and then logarithm absolute value of x and evaluation from 1 to b. So that is same as now limit. Okay, here logarithm b, now minus logarithm 1, which is 0. Okay. Now, b is approaching infinity, so that the value must be infinity. So when p is 1, the integral diverges. Now, how about the other case? Secondly, here now, p is not 1. Then the given integral can be written here, same limit here, b approaches infinity, and from 1 to b, and 1 over xp can be written x to the minus p and dx. Okay. Antiderivative of that one is same as here, minus p plus 1 is reciprocal times here x to the minus p plus 1. So here, same limit. And then now that is 1 over and 1 minus p and x to the 1 minus p, right? And then we have evaluation from 1 to b. So here, this same as a limit, the same limit, and then there is 1 over 1 minus p, and then once it is b, then b to the 1 minus p, and once b is, x is 1, then there is 1, right? Okay. Now, if 1 minus p, for this one we have two cases. If 1 minus p is positive, then now x approaches infinity, then positive power, it goes to infinity, so it is diverges, right? Okay, and 1 minus p is negative, then b goes to infinity, then it will go to 0, so that it is converging to here minus of that quantity, so which is now 1 over p minus 1. So this condition is same as p is larger than 1. Okay, we write down here, if p is larger than 1, then the limit is 1 over p minus 1, so it is convergent. So it is convergent only when p is larger than 1. Okay. Determine whether the integral converges or diverges. Okay. For that one, the domain is infinity. So exactly the same way, we can do limit b approaches infinity and 1 to b integration. Now, before that, this one is now a proper rational function, so that we may try to use a partial fraction technique. Okay. For integrand, that is same as 2 over, now factors are now x and x plus 2, right? Okay. So that can be a over x, and another part is b over x plus 2. We have to decide a and b. Here, common denominator is x and x plus 2. And here, now there is a and x plus 2. And now for second part, it is same as bx. Right? Okay, from here, now the coefficient of x term is a plus b, and the constant term is 2a, and here divided by the same denominator. Okay, that must be same as 2, which means that here a plus b must be 0, and 2a must be 2. From here, a is 1 and b is minus 1. Okay, so the given integral can be written here limit and b approaches infinity from 1 to b. Now, we rewrite this one by using these partial fractions. So 1 over x minus 1 over x plus 2 dx. Right? Okay, for that one, same limit, and antiderivative with this one is logarithm x, absolute value of x, and now for this one, that is the logarithm of x plus 2. Okay, so along with that negation, we can write here logarithm and x over x plus 2, right? And then we have to evaluate from 1 to b. Okay, so here that is the same as the same limit, and then logarithm of b over b plus 2, and now minus logarithm is 1, then logarithm of 1 over 3. Okay, so now once b is approaching infinity, then this quotient approaches 1, so the value becomes 0. So we have here minus logarithm 1 over 3, so it is the same as logarithm 3. Okay, so the final answer for this problem is that the improper integral converges to logarithm 3. Okay. Now we'll see another definition. It is for the case when the integrand is not finite. So here, f of x is continuous on a to b, excluding a, and at point a is discontinuous. That means that here at a, the value goes to infinity. Then here we'll try to take the integral from c to b, and then we take c approaches a from right side. Okay, let's see picture here. Now here there's a, and this is a b. Now here at a, now function value is blowing up so that it goes to infinity and find it like that. Then we try to take integral, evaluate integral from c, and then the value is bounded. So range of function over c to b is bounded and finite, so that we can get the integral by using a conventional technique. And now after getting the integral as a function of c, we now push c to a from the right side. That is exactly that one. So in this way, we try to get the improper integral of type 2. Okay. Now, once the function value is infinity at right end, then similarly, we try to get the integral up to c, and we here take a limit as c approaches b from the left-hand side. Now here, for this case, now somewhere between a and b at c, the value goes to infinity. Then we try to compute from a to c the integral and evaluate from c to b, and then both exist. Then here that the sum will be the final answer. Here the same way for type 2 improper integrals, once limit exists and finite, then we say the improper integral converges, and otherwise we say the integral diverges. Okay. Let's see this problem. For what values p does the integral from 0 to 1, 1 over xp and dx converge. Okay, for this one, you can solve this problem exactly same way as for this one. So you consider the case piece 1 and piece not 1 and try to solve the problem. Then now you can do it, just to do it yourself. Okay. Now the answer for this one is that here for this finite interval, yeah, that is now when p is less than 1, the improper integral converges to 1 over 1 minus p. You can check this answer quite easily. Okay, now we'll go here, determine whether the integral converges or diverges, and once it is convergent, then evaluate it. Okay, for that one, here, now, from now on, we'll use limit, and it's a little bit cumbersome, so that we'll try to use here integral from 0 to 1. But once it has the infinite value, then you may consider that it's the same as from c to 1 and limit and c approaches 0. You may think that way. Okay, but for this integrand here, this quantity to power half, so that now if you are making, okay, now you can get change a variable. You may think change a variable, or directly you can get it. Okay, the given integral is same as now. Okay, antiderivative for that one must be x squared plus 2x and half power, square root of that anyway, and along with some coefficient, right? Once, okay, let's try to get the coefficients. And then if you try to make a derivative for that one, then a half will come out, and along with a minus half power. And then derivative of this one will be 2x plus 2. And half and this cancel out, so that it'll become exactly that one, so that the coefficients must be 1. Okay, you don't need any other coefficients. Okay, now for that one, here you can put here evaluation 0 to 1, right? So that once it is 1, then 3, so that square root of 3, and once it's 0, then it's 0. So that the answer is square root of 3. It is convergent to square root of 3. We are using now 0, but that is improper integral. You can do this one. If you want to do this one with using the definition, then you can do this in this way. Limit, and c approaches 0 from the right side, and from c to 1, the integrand. Okay, now that one is same as the same limit, and here antiderivative is this one, so that is x squared plus 2x and half power, and from c to 1. Now there is limit, c approaches 0, and then there's once is 1, then square root of 3, and when this is c, then that is now here, okay, that is a c squared plus 2c and half power. But once c approaches 0, then that will become 0, so that again you will get square root of 3 for the final answer. So this limit and c, it is a little bit cumbersome, so that here in practice, rather than using this one, limit and c, just simply we try to get the value, and with by using the original the limits. Also for that one, it's the same. Here, once it's 0, then it's 0. Okay. Once it's 0, then 0. But infinity, then also the unbounded. So this is improper, and because of two reasons. One is around 0, and now the value becomes infinity, and now the domain is infinity. So here, for this one, you can write in this way. There's from 0 to some point between 0 and infinity. Okay, let's say 1. And here, from 1 to infinity. And for these two portions, you have to get the integral. So here, integrand is here and dx, right? So let's begin with integral 0 to 1, and here 1 over 1 plus x and square root of x over there, and dx, right? For this one, here now, because of that, you have to use substitution. Okay, let's start with u equal square root of x, then x is u squared, and then now dx equals same as 2u du, right? And again, here x is 0 to 1, then again u is again from 0 to 1. So that is from 0 to 1. And here, that is now 1 over x is u squared. So that is u squared plus 1. And square root of x is u. And on the dx is the same as 2 u du. So this u will be cancelled out. And here, and 2 can go out, then 1 over 1 plus u squared is now arctangent of u, so that here 2 and arctangent of u, and from 0 to 1, right? Okay, for this one, now it's 1, then it's pi over, okay, that is arctangent to 1, that is pi over 4 twice, so that is pi over 2. Okay, so we get pi over 2 for 0 to 1. Now for second part, from 1 to infinity, you have to evaluate that. Okay. That is now from 1 to infinity. That is here again 1 over and x plus 1, and now square root of x dx. Now exactly the same way, again, you can use a change variable. Then now it is same as once, okay, along with that change variable, you can get this one. Now this one is here now infinite domain, but anyway, once x is infinity, then u is also infinity, so that is 1 to infinity. And here we have what is that, twice of 1 over 1 plus u squared plus 1 du. Okay, so that is the same as twice of now arctangent and u from 1 to infinity. Okay, so that is twice of, and once it's infinity, then there is pi over 2, and with 1, that is a pi over 4, so that is pi over 4 twice as now pi over 2. So we have 2 over pi over 2, so that now both sides convergent, and then the addition will be the final answer. Okay. determine whether the integral converges or diverges. And for this one, now here, you can get that one quite easily. And of course, over there, at 2, it is the value becomes infinity. But anyway, here you have to write down this one separate from 0 to 2 and the integrand, and then from 2 to 4, right? So case by case, you have to find the n. Now from 0 to 2, there's number 1 case. That is 1 over the integrand, and that one, and dx. Then that is same as, okay, now once x is around just approaching 2, then goes to infinity, but we are using 2 rather than limit and c. It's okay, and because if you write down exactly, then it's a little bit taking time, so that we are using that notation. But you have to understand that this is the same as limit c approaches 2, and that is a c. Okay? Now, what is antiderivative with this one? There must be here some coefficient, and now that is x minus 2, and here third power, right? Okay. Now, once you make a derivative of this one, then 1/3 will come out, so that you have to put here now 3, right? And then here you have to evaluate from 0 to 2. Okay. So this value exists, and once it's 0, okay, right now, okay, that is 2, then it's 0, 0 then minus 2, so that it's 3 times of 2 to the 1/3 power, okay? For the other side, and of course over there, antiderivative will be the same, and evaluation must be from 2 to 4, so that you can imagine that here, this side also convergent, because antiderivative is no problem along with 2 and 4, so that it must be convergent, and you can find the other side and then add the value to get the final answer. Okay. Okay, and here so far we'll try to get the value, and then by using the limit, we try to evaluate the improper integrals, but sometimes we cannot evaluate the improper integral by using here integration techniques. And in this case, first we have to decide whether the improper integral converges or diverges. If the integral diverges, then that's end of story, because even though you try to get the value by using some other technique, and the value will be infinity. And if the integral converges, then we may try to use some numerical technique to get the value here. So we have to decide, we have to test the integral if the integral converges or diverges. We have two major testers: direct comparison test and limit comparison test. Okay, this one is direct comparison test. Let's see here. f and g are both non-negative and g is larger than or equal to f, then if larger one, integration of larger one converges, then smaller one should converge. Because this is convergent means the integral is bounded, so that the smaller one should have a bounded value. Now, the second part is once the smaller one diverges, then here automatically larger one should diverge. Quite reasonable, right? And we have a limit comparison test, and f and g are continuous, and we assume positive and over infinite domain, that if f of g, the fraction has a limit L is non-zero, positive, and also finite, then here these two both either converge or diverge. Once one of them is convergent, then the other one should. And once one of them diverges, then so does the other one. So that is limit comparison test. Okay, here. Now we'll try to show that that is convergence. Now, that is two issues. When x is approaching 0, then the value goes to infinity. And now the domain is infinite, so that we have to consider two portions. The given integral can be separated in this way. There's now from 0 to, okay, let's choose 1 here. And now plus here from 1 to infinity of the integrand and dx, right? Okay. So and for this region, we have to test. We cannot get the value because it's not elementary derivative, so that it's not easy to get antiderivative. However, we can see if it is convergent, so that in fact it is convergent, so that it is asking you to show the integral converges. Okay, so here we have first we consider the interval from 0 to, of course 0 at 0 is not defined, so that is from 0 to 1, okay, over the interval. Now the integrand is here, that is 1 over square root of x plus x cubed, that one is now, okay, because we have to show that this is bounded by something, so this something integral is bounded. So we may choose here, that is, for example, square root of x. So in the bottom, because of x cubed, if we consider only bottom, then this side is larger, and it's reciprocal. Now that side is larger, right? Now, integral over 0 to 1, integral over 0 to 1, but we already know that integral from 0 to 1, 1 over x to the p dx converges when here p is less than 1. For this case now p is half, so that the integral of that one is convergent, so that it must be convergent. Okay. Now secondly, here now we are considering here from 1 to infinity. Then 1 over the given integrand, 1 over x plus x cubed. Okay, we have to find something here, and it's larger than or equal to this one. That is now 1 over, for example, now and okay, square root of x cubed. How about that? Then once we consider only the bottom, then this side is larger. Now it's reciprocal. That side must be larger. And integral over 1 to infinity, integral over 1 to infinity. Now we know that here from 1 to infinity, 1 over xp and dx is convergent when p is larger than 1, right? So that this p is 3 over 2 larger than 1. So the integral over 1 to infinity converges. So it should be also convergent, right? So both sides convergent, so that eventually whole integral must converge. Okay. Use integration, the direct comparison test, or the limit comparison test to investigate the convergence of these integrals. Okay, for that one, okay, I selected 30 problems here. For the first one, you can use integration technique, and for that one, direct comparison test. For that one, limit comparison test. I'll give you only some hints. Okay, for that one, now around 1, x is approaching 1, then the value logarithm x approaches 0, so that the value goes to infinity. Now here, if you try to get the integral, then c to 2 and limit c approaches 1. But anyway, in any case, is the antiderivative of this one is the same as now logarithm, okay, and logarithm of x, right? So that if you make a derivative, then so on the bottom we have logarithm x, and that derivative is 1 over x, okay. So that's antiderivative. And here from 1 to 2 evaluation. Once, in fact, you have to put here the absolute value, and again here absolute value, right? Okay, now once it is 2, then it's okay. But here, once it is 1, then this value becomes 0, so that now logarithm 0 is infinity, so that it is divergent. Now for that one, yeah, part 2, yeah, from e to infinity in right and here infinite domain, infinite interval, okay, we can see easily, okay, logarithm of x is smaller than, okay, we put here equality, but anyway, way smaller than, in fact, x to the p. For example, p is half square root of x. This is, you can check this one quite easily by using the ratio logarithm x over square root of x. Then as x goes to infinity, infinite over infinite shape. Now by using L'Hopital's rule, you can check that it's converging 0, which means that even p is larger than, slightly larger than 0, anyway, logarithm x will be smaller than square root of x. Okay. Okay. So here, if you take reciprocal, then 1 over logarithm x, and now that one is larger than or equal to 1 over square root of x. Now, integral from e to infinity will diverge, so that one should diverge, right? Okay, for that one, once the problem is around the 4, it's okay, the value exists, and then Now, from 4 to infinity, for any fixed point, this one is not going to infinity. So it's okay. But the problem is this limit, infinity. Okay. But here, so when x is growing, then the major term is this one. So that, let's see in this way. We consider the given term is f, and we consider another function g along with this major term, 1 over here x to the 30 over 2. Then, now f over g, that one is the same as now, okay, that is x to the 30 over 2 over x to the 30 over 2 minus x. Now we take a limit, okay, limit x approaches infinity for this quotient. Then we can easily see that it's approaching to 1. Its highest power is this 2, and coefficients 1 and 1, so that the value is 1. Now, so that the convergence of this one is same as convergence of integral of that over the same infinite interval. But we already know that this p is larger than 1, so it is convergent. So this should be convergent, right? Okay. Okay, that's the end of the review for chapter 8. Thank you.